Look at a world like Pandora, towering canopies pulsing with blue light, an entire ecosystem glowing in the dark, acting as one giant living network. For decades, the scientific consensus was that if we ever found life out there, it would be microbial sludge clinging to cold, dead rocks, leaving the vibrant, lush paradises strictly to the movies. Directors and concept artists designed these environments using pure imagination, unbound by the limitations of observational data. Data coming back from our newest space telescopes reveals that these cinematic environments are actually grounded in real math and physics. Finding the specific atmospheric and geological conditions that support complex ecosystems is the primary objective for the next generation of orbital observatories. Astronomers are now using these cinematic models to refine what they look for in deep space, turning creative speculation into a technical checklist for our next discoveries. Kepler 452b is Earth's supersized twin. When you have a rocky planet this massive, you have to ask if the towering aliens and floating landmasses we see on screen could exist on its surface. This diagram compares the gravity wells of Earth and a massive super-Earth. A planet's mass dictates its gravitational pull. That pull determines how dense the atmosphere becomes, setting the rules for how mountains form and how biology evolves. This chart highlights the relationship between air pressure and mineral density. In a world with a high-pressure atmosphere and low surface gravity, the upward force of displaced gas, buoyancy, could offset the weight of certain porous rock structures. Under these specific conditions, landmasses could lift and drift within the atmosphere. The life forms breathing that thick air would have to adapt. To move efficiently through an incredibly dense atmosphere, a biological entity would evolve to be much taller and leaner than a human. The physics-defined landscapes and oddly proportioned creatures we watch in theaters are logical manifestations of astrophysics operating under a different planetary mass. Standing on the surface of one of these moons, the view directly above you would be entirely alien. The TRAPPIST-1 system provides a clear example, operating like a highly compact 7-world ballet. This diagram shows the top-down view of TRAPPIST-1. It maps out compact orbital mechanics, demonstrating how you can pack 7 distinct Earth-sized planets incredibly close together around a single star. Because these orbits are compressed into such a tight space, the distance between neighboring worlds is drastically reduced. Looking up, you wouldn't see distant pinpricks of light. You would see massive, detailed spheres dominating your sky. The visual of a giant sibling world hanging over the horizon is a mathematical certainty in compact planetary systems. The closest chance we have to see this up close is Proxima Centauri b, sitting just 4 light-years from Earth. This animation shows what happens when a planet becomes tidally locked. Its rotation syncs with its orbit, leaving one hemisphere blasted by eternal radiation and the other plunged into permanent, freezing darkness. Between those extremes lies the terminator line, a thin, permanent twilight zone wrapping around the planet. This is the only place where temperatures are moderate enough for liquid water and life. To study this region, astronomers use spectroscopy, analyzing the specific wavelengths of starlight passing through the atmosphere to detect biosignatures that indicate living organisms. Flora or fauna evolving in that perpetual twilight would have to adapt to the dim light. To communicate, hunt, or attract pollinators, these organisms would mathematically require bioluminescence, the ability to produce their own light. Neon glowing jungles are a hard evolutionary requirement for survival on the most common type of habitable exoplanet in our galaxy. If the universe is mathematically teeming with these vibrant, habitable worlds, the lack of any radio signals or communication remains a profound, unexplained silence. Percolation theory offers a leading astrophysical explanation for this absence. This galactic grid illustrates how civilizations might expand until they hit physical barriers, vast, empty cosmic dead zones. This leaves intelligent life clustered in isolated pockets, cut off from one another. Humanity is now building the technology to cross these dead zones ourselves. NASA and initiatives like the Breakthrough Starshot program are developing light-propelled nanocrafts. These are small solar sails pushed by powerful lasers, designed to travel fast enough to reach these exoplanets within a human lifetime. The focus has shifted from wondering if these worlds exist to the engineering required to reach them. The race is on to see these distant Edens with our own eyes.